Okay, so it should work now. Okay. Okay, so one more time, welcome here. This is the second part of the this double kind of lecture, because the first one was just the most time taking, or I think it was just about 3 hours. I told you before, do you know? But this one will be really short because I prepared only 14 slides, and some of them are really quick. We can went through them. We can go through them very quickly. And yeah, so what I'm going to talk about for today, it will be just a quick introduction to some medical decision making. And for the very beginning, I would like to say that it's just a kind of topic which is relatively complex, and there's no something like, for example, a textbook from which we can extract some important pieces of information just to put them in the slides, in the frames, and talk about them with you. Yeah, it's just a kind of complex, let's say, topic, such that there are some papers on this, but their number is also limited. So there are, as far as I know, there are no good textbooks on this. Some of them are just done by Professor Cox, but yeah, these are good, but these are more into mathematics. So I just tried to extract some, let's say, more applied pieces of knowledge you should know about, or it'd be better, for example, or at least it would be interesting for you. So I tried to do this, and now I'm going to talk about it. So really more about medical decision making and under some, let's say, point of view of let's say, applied probability. But don't be scared by these terms. I'm going to make it, well, let's say, very applied. So I'm just going to go through some let's say, daily routine examples from applied medicine, from the daily practice, so we can do it in this way. I think it will work. Okay, so for the beginning, there are some pieces of motivation and some pieces of basic terms, let's say. Okay, what is absolutely clear for the beginning, I have no doubt that you know about it, or you at least thought about it exactly the same way, is that all the medical decisions which physicians are supposed to do, they are by nature, by definition, so they are inherently uncertain, and they must be inherently uncertain, because of course, I mean, just at the moment, at the decision moment, at the moment of the decision making, because there are too many factors which are unknown at the moment of decision making, that in consequence all the medical decisions are naturally in uncertain, and there must be uncertain, and this is like a fact, and we have to work with this fact. So what are also other facts or motivations why we should know about some, let's say, good practice, how to deal with let's say, this kind of uncertainty, how to, for example, do the decisions, let's say, better than, for example, only by some experience, or some, yeah, by some experience or by some feelings. I don't want to say that your future clinical experience or your future clinical intuition or feelings or some ways, it's not a better thing. It's definitely, in fact, it's just a good thing. And I talked about this last time, that evidence-based medicine is partly based also on a clinical physicians' experiences. Yeah, that's definitely something which is also important. But sometimes, of course, a physician could be, let's say, mistaken by his or her, let's say, feelings, or let's say their intuition could be, for example, confused by some, let's say, not so much informative symptoms or something like this, and that's why there are some, let's say, rules which could be recommended, and I'm going to talk about them. So other pieces of motivation which are here are the medical examinations or diagnostic tests are, of course, imperfect. It means that we have no perfect diagnostic test. It means that there are both kinds of errors we could think about. For example, the first kind of error is that we have, let's say, patients with no disease, and these patients are going to undergo kind of test, diagnostic test, and they have no disease, but still the test is going to show for them as a positive one. So this is like kind of error, definitely kind of bias, because they have no disease, but the test test says that they have disease because the result of this test is positive. This is the first cycle error, and the second kind of error is that we have patients with disease. Okay, for example, it could be confirmed by some golden standard methods, or it could be simply proven by time. Yeah, for example, at a decisive moment, we have no possibility how to confirm. But for example, after 1 or 2 years, there could be absolutely no doubt that patients have the disease, they have had the disease at the moment of decision making, because yeah, for example, they are going to, for example, develop some yeah, I don't know, some consequence symptoms, consequence, for example, yeah, some consequence, let's say, comorbid yes, pathologies and ongoing pathologies and something like that. So the second kind of error is that we have patients with disease, and they have the disease, but the diagnostic tests are going to fail, so they are going to show for them that like they have noticed, or the results of this test are negative. Means that simply it seems that these people are healthy. So this is the second kind. This is just the second kind of error. So saying this, definitely both the medical explanations and the diagnostics are imperfect. Diagnostics are imperfect in the manner I just said, and of course, medical examination is kinda subjective. Yeah, it's also based on some experience. So I would say that something like a sensitivity or specificity of medical examination done by, for example, a physician by practice could be even worse than, for example, well-established diagnostic tests. And also, I don't want to say that like a physical medical examination is a bad thing. Definitely, it's just a basic thing. We have to do it, for example, on daily routine. Definitely, it's important, more than important. But now, still, that medical examination is something which is okay. It's kind of just a very basic stuff we should do at the very beginning of the diagnostic or therapeutical process. But definitely, it's usually not enough, for example, to do some more complex diagnostics or something like this. Also, what was to be mentioned is that both the indication rules, or for example guidelines, okay, these indication rules are, I would say, they are sometimes very vaguely defined, or I would also say that, for example, their definitions are they are based, for example, on some, let's say, good practice which is limited, for example, to some department. Yeah, and it could work, why not? Yeah, but for example, this is, for example, not so much reproducible, and it's, for example, not so much based on some current published results or current literature references or something like this. But still, it could work. Yeah, but it also means that, for example, the department could do something like a cost benefit analysis, and that, for example, sometimes there could be some bad habits, for example, for example, not to offer some kind of drugs to patients who need them, because of, for example, simple of saving of money, for example, something like this. It's relatively usual as far as I work on a clinical department. I know that this is a relatively usual bad habit of I would say department, not only here in Czechia, but I would like all around the world, because I worked for a month or 1 month in Egypt at like the country hospital in Egypt, which was absolutely the same. Yeah, I would say, I mean just the manner, yeah, not for example the level of the level of, let's say, the medicine. It was rather good, yeah. But like the, for example, the pragmatism of saving money, for example, was not to offer some drugs to some people. It was like absolutely the same as, for example, here as in Egypt. Okay, so guidelines. The next thing, guidelines. Sometimes guidelines are simply missing. And this may be the thing I said to you during the last lecture, because, for example, about the guidelines here in the Czech Republic, there are usually some guidelines, and some of them are usually written in English, but maybe it doesn't matter, yeah, because the vast majority of physicians here in the Czech Republic are still like the Czech natives. So I think it's enough that they are written in Czech, but that's not a problem. Yeah? That's not the thing. That's not the point. The point is that the number of guidelines are still very limited, but okay, it's like the okay, maybe it's increased by time. Usually, I would say that this is like slowly increased by time. But the problem from my perspective is that uh, whereas they are just the guidelines, they are not applied so much, yeah, in the practice. But and what is like usually applied is like the let's say empirical indication rules or something like that. Yeah, indication rules based on good experience, a good practice of some let's say departments, and so it simply works like based on their good experience. And I would say that it could work, yeah. But if there are some guidelines, for example, which could have some additive value or something like this, this is maybe something which would be better to at least to try it. Okay, another motivation or another kind of clinical issue which is rather often frequent is that in many situations, for example, we have some kind of special situations such that there are no, let's say, clinical references or literature references, or for example, clinical diaries, and you know the clinical diaries are just the best designs, best possible designs of clinical, let's say, studies. So the well-defined clinical diaries are not available, or they are just simply hardly generalizable to our, for example, situation. It means that there are, for example, some references on some clinical trials which are related to our problem. So we have some patient with, for example, special syndrome or special, let's say, bunch of symptoms, but still the clinical trials are, for example, maybe more general, and it could be, for example, so much well applied to our situation. So this is also the reason why the thinking of a physician is usually probabilistic, and all the medical decisions are uncertain based on this pieces of let's say or these issues which are uh, typical for daily practice of physician, regardless if it just works here in Czech Republic or, for example, in USA or wherever. Yeah, it doesn't matter. So how to try to navigate through this, let's say, uncertainty. There are some tools we should know about, and they include some, let's say, apparatus like probability theory. And one more, don't be scared by this, let's say, more mathematical, yeah, probability terms, because I'm going to talk about it, but not like in a so much doubt way. Yeah? So don't worry. So probability theory, some threshold theory, explicit value decision analysis, and some others. I'm going to talk about some of them because I just went through some papers which were interesting, and I just try to extract important pieces of knowledge you should know about, and that's the thing. So definitely we are not going to cover these topics and its complexity because it's not possible. I would say that it would be just a 2 semester kind of subject. This is a kind of course just to cover, for example, majority of this complex, really complex topics. So we are going just to go through some selected, let's say, issues and some selected rules or recommendations which we should follow or which could be followed just to, for example, overcome some, let's say, decision troubles. Yeah. Okay, so it was our motivation. So let's go to probability rules. I think I'd say that this is maybe the most important part of this lecture. So uh, definitely don't be scared by this formula or whatever, because I'm just going to go through it. It's just simple method. It's just simple arithmetic. So don't worry about this. So what is the probability, and what is the motivation for using probability? Because honestly, I would say that that's absolutely no necessary to use probability on a daily practice in your, let's say, future practice. It's not like about this. I don't mean it by this, but sometimes, because I would say that, let's say, 60 or 70% of situations we are going to handle with, or you're going to deal with, they will be like, for example, very common for you. It means that it will be absolutely clear what to do, what not to do, and so on and so on. So uh, in such a case, there's no need to apply to this kind of, for example, tool or whatever. Yeah, it's not it's not necessary. But for example, in some special kind of those special cases, like for example, typical case which was like the first one, such that there were some more concepts or models for example, computer-aided decision making, or just computer-based decision making. It was just a chronicle, I mean, just chronicle long-term back pains, because back pain is something which is usually not related to, for example, some emergency situations. For example, it's not like a threat of, for example, life, not something like this, but definitely it's uncomfortable for a patient. And for example, it could take simply long years, and also the diagnosis, what is the reason, and for example, what should be the appropriate treatment is could also take many time. So yeah, this is, for example, the kind of situation where some kind of probability models could be applied just to help the decision making and help to, for example, to decide what to do, for example, as a first thing for diagnostics, as a second thing, and after the diagnostics part, for example, how to start a treatment and so on. Okay, so in daily practice, that physicians usually use the words like frequent, possible, unlike, or rare, or whatever. They use it like in order to quantify, for example, some, let's say, phenomena or symptoms or whatever they deal. And these words, based in common English, they are simply here just to estimate the kind of the level of uncertainty. But for example, if we have two physicians, and one of them is just simply can use the frequent, for example, for kind of symptom, which is, for example, in 60% of patients with a given disease. And the second physician, for example, could use the term frequent, for example, if it's just in a 99%. It is if the symptom is presented in 99% of patients with the given disease. So this is like definitely this is subjective. So it's based on both the experience or the physician and on some, let's say, feeling, also some language feeling for English and so on. It's based on several things like this. So this it could become sometimes very confusing. What means what is something is a frequent symptom, or possible, or unlike, or rare. Yeah, for example, it could be sometimes a bit confusing. So just in order to overcome this confusion, which simply arose from the fact that these are just the layman English words, we can try to define or quantify the frequencies using probabilities. So so I'm just going to define what is a probability, and I'm going to use the first kind of definition, because since I got a master's degree in statistics, I can tell you that there are at least 4 different definitions of probability. This is like the first one, the most, just the oldest one. Yeah, based on a scientist called Laplace. He's a French scientist. I would say it's something like a 17th century. And this one was based on some card games which were very famous in the 17th century in France, and not only in France. And it was based like on the fact that if we are just some event A, and event could be, for example, in the context of medicine, for example, if a given patient, for example, has a disease based, for example, on the fact that the patient has some bunch of symptoms, something like this. But in general, let's suppose the event A, and probability PA describes how likely the event A is to occur. So this is like let's say, like an integral kind of definition. And the probability PA is simply equal to the number m of cases which are favorable for the event A over the number n of total outcomes. So it's simply just this kind of fraction, this kind of a ratio, m over n, of ratio m to n. Yeah. So for example, if we have a coin, and so we try to consider the coin tossing, you know that there are only 2 possible outcomes. Like it could be just a head or a tail on the upper part, which is upper side of a coin. One is simply just tossed. It means that we have 2 possible outcomes. So n is equal to 2, so which is n in the denominator. And for example, if the event A would stand for the situation that head is tossed. It means that there's only one favorable case. It means that it's a one for the head, yeah, which could be tossed. So it's a 1/2, 1/2, and that's simply the probability, which is let's say commonly known from a common sense that probability of head tossing is simply 1/2, and also the probability of tail tossing is simply 1/2. This is also 1/2. And by this definition, I think it's pretty easy to get the insight that this fraction, which stands for the probability PA, is somewhere in between the range 0 to 1 inclusively. Because yeah, it could be a positive, it must be positive number or 0, yeah, because if the M and R are simply numbers, like the counts of cases, there's there's absolutely no way how it could get the negative value. So that's the first insight, and the second insight, it couldn't be larger than 1, because there are total outcomes. Number n stands for total outcomes. It's absolutely it's more than clear that the number m cases which are probable for the event A, simply the number m couldn't be larger than the number n. So it could be at maximum probability could be equal to 1. And probability equal to 1 stands for the situation which we can be 100% sure that it will occur. And on the other hand, probability equal to 0 stands for an event which we can 100% be sure that it's not going to happen. So it's as easy as this. So yeah, just in a daily practice, the probability. Okay, there are several ways how to get the probability, for example, of an event, and the event could be, for example, a probability, just a level of confidence of a diagnosis, for example, based on some symptoms, for example. So how can you probability in daily practice estimate it, or how can you get the probabilities? Okay, I think once you start to do the medicine, the applied medicine, I think that, for example, after several years in, let's say, applied medicine, you are able to say what is, for example, let's say, for example, which diseases are frequent, which diseases are not so much frequent, which are very rare, and so on. So, for example, yeah, or similar to, for example, treatment and so on. So based on this, based on your personal experience, the probabilities of events, I mean, probability of diseases, probability of some diagnosis, they could be estimated simply subjectively based on a physician's experience. I think it is the most common way how to get, for example, some feeling of, for example, if the probability is large enough, high or low, or something like this. We also adjusted by some published references, so by some literature. I'm just going to talk about it like in a few words. The last part is about database, but this is pretty simple. These are only 2 databases which are based on quantitative kind of evidence. So I just mentioned, I just listed these 2 databases here, but this is what I meant by this note here. It will be adjusted. Okay, your personal feeling, your personal experience, for example, that this kind of disease is relatively rare, or for example, this another kind of disease is relatively often, relatively frequent. There it will be adjusted by some published references. For example, there could be some papers, for example, just to analyze what are the prevalences, or prevalences are pretty the same like probabilities here, but prevalence is like more epidemiological term, but in fact, these are absolutely the same. So the prevalences or probabilities of diseases could be, for example, analyzed in context, or for example, under some, let's say, considering some other kind of factors. For example, let's say they could be the probabilities could be, for example, differ between sex, or for example, age periods or something like this. So the published references could make the better idea what could this be about. What is also typical is that this situation with that there is absolutely no such kind of problem published yet. It could happen definitely. In such a case, Yeah. I mean, okay, it's a okay. Maybe this there are 2 points. The first point, if it's just simply not, if it's simply not published, you can try to, for example, search for some similar literature, and try to, for example, yeah, just try to get some first insight or first impression by at least reading the similar, yeah, similar version. Try to generalize it, for example, to adjust it, let's say. But if there are, for example, yeah, if the situation is not published like precisely exactly the same, then you could adjust the closest published result a bit, because nowadays I think there are too many papers. For example, if we are going to talk about COVID, I think nowadays there are 40,000 of papers only about COVID. You know, the COVID is something which is maybe less than 1 year old issue in medicine. Definitely, it's a severe issue. It's a serious issue, of course. But just in a time which is shorter than 1 year, there are 40,000 of papers dedicated to, I mean, impacted papers dedicated to COVID. So it's like a enormous value, enormous amount of papers. So what I wanted to say is that in general, there are a very, very large number of papers dedicated to various kinds of medicine. So I would say that there is it will be just a very rare if there will be just situation in medicine such that there are absolutely no papers about it. Yeah, I bet yeah, I bet my chances that at least 1 or 2 papers we are able to find 1 or 2 papers, for example, related to a situation you would like to know about, or for example, you have to deal with. Okay, it could be, for example, somewhat similar, somewhat related, not so much exactly, but somewhat. But still, it could get you some, let's say, better information about the organization. You can, for example, adjust your feelings about what could be the prevalence or probabilities be about, yeah, something like this. So you can try to, for example, adjust your feeling up or down, just looking for the individual characteristic of the patient. Because if you know, for example, that it was just, you know, that, for example, we have a patient with a bunch of symptoms based on the literature based on references, for example, the probability of some kind of disease, for example, 0.1, 10%. But for example, you can see that the patient is, you know, which is overall in general is, for example, in good shape. Yeah? It means, for example, it's for example, and if you consider that the disease is relatively serious, not severe, for example, it's somewhere against the assumption that or against your observation that the patient is like in general in probably good shape. So you can just try to adjust down your feeling that or your estimated probability that probably get the disease, for example, from 10% for example, to 5%, something like that. So you can try to use your yeah, just try to just do the common sense or your let's say experience and simply your intuition, yeah, just to adjust this just the published numbers, published probabilities. And why this is important, I'm just going to go slowly towards the some formulas we are going to work. And there are, okay, there are maybe two or three, okay, two, let's say, calculation examples. I'm just going to talk about them, and they definitely use the numbers, so that's why it's also important to know the numbers. Well, so what I'm going to talk about now is just Bayes' theorem. Maybe I believe that some one of you already heard about Bayes' theorem. At least if you, for example, watched the I just forgot it. Yeah, if you watch the Big Bang Theory, definitely you know about Bayes' theorem. Yeah. And this is like a kind of form of Bayes' theorem which is called the odds ratio form of Bayes, because which is the simplest one. So that's why it could be, for example, easily applied, for example, without any hard calculations. So what does it mean? What is a Bayes' theorem, and what is the odds ratio of Bayes' theorem? So so considering that the symbol P stands for the probability of an event, and also the event could be, for example, a disease or diagnosis or something like this, then the fraction P over 1 minus P is the odd that the event will occur. So One thing is the probability, and you know the probability is defined like this, and the probability is somewhere in between the range of 0 to 1 inclusively. But the occur, the odd is something a bit different. And there is just an example for you. Here, the value of the tossed head, of the tossed head, while the coin is tossing. And we know that if it is a unbiased coin, it is fair coin, you know that the probability of the tossed head, the head will be tossed while the coin tossing is exactly equal to 1/2, so 0.5. And if we know that the probability is equal to 0.5, then the odd that the head will be tossed is p over 1 minus p. It means that this is a 1/2 over 1 minus 1/2, which is exactly equal to 1 over 1. And it could be also written in this form, following this form, one colon, one colon 1 or 1 to 1. Simply, it could be read simply 1 to 1. So odd is 1 to 1 when probability is 0.5, and probability is 1/2. So it's just, in other words, it's just let's say a bit different way how to express the probabilities, rather in the form of the odds than in the natural form of probabilities. And the form of odds are better to be used for the Bayes theorem, because the Bayes theorem follows this formula. But before this formula, I just wanted to say that this line is also important, because this is exactly why this is important. Why this formula could work. If we know that the probability p must be somewhere in between 0 to 1 inclusively, and that's pretty clear because I talked about it in this definition by Laplace discrete probability. Yeah, that's by analyzing the properties of this fraction, definitely we'll just get this this inequalities. So if we know that these inequalities are true, then we can try to derive that the odd might be somewhere in between 0 to infinity. Infinity. So because if p is somewhere in between 0 to 1, we are going to get the fraction p over 1 minus p. It still have to be a positive number, because 1 minus p could be 0 from 0 to 1. This is positive, so both the numerator and denominator are positive, so it has to be positive. It could be also 0. In case that the p is 0, then it's going to be p 0 over 1 minus 0, so 0 over 1, it's equal to 0. But for example, when the p is really large, for example, it could be something like 0.99. So it will be just 0.99 over 1 minus 0.99. It means that it will be 0.99 over 0.01. So it's something like I don't know, something like 99. Yeah, 99 maybe. So for the more is the closer is the p to 1. The closer is the p to 1, the highest value the odds could get. Yeah. So it could be almost it could tend to infinity. And this is important because if we are able to transform probability in something which is positive, but it could be whatever number somewhere in between 0 to infinity, we can apply this kind of formula. If we know the pretest odds, let's say like the initial estimate of odds, it's not like probability but odds, but we can transform the probability to odds by this formula. It's as easy as this. So we have the pretest odds, and we can try to just something which is called prior estimate. We multiply by likelihood ratio. I'm going to go on this like worked out example by likelihood ratio, and we are going to get post-test odds. It means that something the pretest odds is called prior, and the post-test odds is called posterior. Yeah, prior and posterior. So the prior, it will be also defined rather in some information way, like the prior information and posterior information. So this is just the information we had at the very beginning of the situation. There's something like a modifying factor, which is called likelihood ratio, And this is the kind of information, or the posterior information, so kind of information we got after this calculation, so after, well, let's say, receiving this kind of information, this piece of information. And like following this formula, it looks like a very theoretical thing, but we can try to go through this example to get it, let's say, more applied. So I think you can see, we will see that it could work. It could definitely. It's not something we are going to do like on daily practice, but for example, in some very, for example, difficult cases, very complex cases, it could work. It is kind of so it's just an applied example of the Bayes theorem. So let's consider we have a patient with acute low back pain. As I told you, low back pain, okay, it could be both acute or, for example, long-term, chronic. It doesn't matter. But if we just acute, if the issues are acute, it could be more emergent for a patient than the long-term. But it depends. It depends. Medicine is not a black and white. It's not a black and white kind of science. So we have a patient with acute low back pain, and considering this, the prevalence of surgically important disc herniation is about 2%. So you know that the surgically important disc herniation is something which is definitely a serious situation for a patient, because if, for example, block or for example, press, for example, for some kind of, for some peripheral nerves, like for example for nervus phrenicus, and so it could, for example, be absolutely emergent, for example, in case that it could press the nervi phrenici, both the phrenicus nerves, which could affect the ventilation of the lungs by just by diaphragm movements and so on. So it could be very important, a really severe kind of situation. And so concerning a patient with acute low back pain, like this is just a kind of published reference that the prevalence of surgically important disc herniation is about 2%. Okay, it means that 2% is not enough. 2% is okay. It's not like very likely. 2%, okay, one patient from 50. It's not like something which seems to be very likely. But let's suppose that the patient also got a sciatica. I believe that you know what is sciatica, but it's a pain which is going down to the leg from the lower back. It's a kind of, it's a kind of injecting pain, pain which is going down very quickly and very intensively to the leg from the lower back. So we know about the patient two things. He came to us with acute low back pain. So if we know only this piece of information, we could think about it that the prevalence of surgically important disc herniation is only about 2%. Not enough, not much. But also, for example, after some physical examination or some anamnesis gaining or something like that, we got also the piece of information that he simply told us that he also got this kind of pains. So we know that he got sciatica. And if there's a combination of these two symptoms, so like a general low back pain, acute low back pain, and also the sciatica sort of pain, which goes simply down to legs from the lower back, it increases the odds of the herniation, disc herniation, important or severe disc herniation, by a factor 8. And how to calculate with the factor 8? So what was the initial odds? Additional odd. The initial odd was, if you know that the initial probability was just simply prevalence, but as I told you, prevalence is like exactly the same as a probability, but the term prevalence is used by epidemiologists, but and the probability term is used by statisticians or other biostatisticians, but their meanings are absolutely the same. So we know that the prevalence, I would say that in medicine, I think that the term prevalence is maybe most common than probability, but their meaning is absolutely the same. So the initial prevalence was just 2%. So we can transform 2% following this formula to the odd. So if we know that probability was 2%. You can follow this formula, like 2% over 1 minus 2% is just 0.02 over 0.98, and dividing by numerator by the denominator, we got result as 1 over 49. Yeah. So it's just the odd, the initial odd. And following the Bayes theorem, the odds ratio form of Bayes theorem, like this formula, we know the pretest odds, just the initial odds, it's just a 1 over 49. We also know the likelihood ratio. As I told you, likelihood ratio is something like a number which could be considered as some number of some additive piece of information, or a piece of new information, something like this. And this is absolutely the piece of new information for us was just that the patient also got, besides the acute low back pain, also the sciatica, the injecting pain, yeah, just the propagating pain. And the factor is 8. So the likelihood ratio is equal to 8 in our case. And both these numbers, like the prevalence and this factor, they are they could be so you can find them in literature. Yeah? Because I found both the numbers in one of the papers. I can try to reference them, for example, the papers after the lecture. So I found both these numbers. So this was also the initial odds was just this, and now we can follow this formula like this, Bayes theorem. So if we does after it is known that the patient has the sciatica, so not only the acute low back pain but also the sciatica, then we can simply calculate the initial odds multiplied by the factor 8, which stands for likelihood ratio, and we got something else which is somewhere around 0 over 66, and this is also odds because this is equal to post-test odds. Okay, post-test also like, yeah, just the posterior, I would say posterior odd, yeah, posterior odd. And it could be also transformed to probability by reverting this formula. If we know the odds, we can simply transform it to probability by calculate 1 over 1 plus the, and I'm sorry, this is like, I would say this is like a typo. There should be also only 1 over 6. This typo, sorry, I just typed 6, but it was written 2 times. I'm sorry. There should be only also 1 over 6. Yeah, so 1 over 6. So there, it was just it was doubled by a mistake. Okay, 1 over 6. So 1 over 1 plus 1 over 6, 1/6. It means that it's equal to, yeah, so 1 over 7, something like this. It's 0.14. So at the very beginning, we knew that the general prevalence of surgical discrimination was about 2%, but now by taking into account the fact that the patient also got the sciatica kind of pain, we can we calculated that the probability of the important or surgically, for example, important kind of discrimination is about 0.14. So it's maybe 7 times larger now. It's 7 times larger than it was before. Still, I would say that 0.14 is still something which is not like it's not so high number, but definitely it's 7 times higher than it was in the very beginning. So we can see that the sciatica is something like a game changer here. For example, if the patient have only like something like a indifferent acute low back pain, still the prevalence of the surgical discrimination was about, let's say, 2%. But since he told us that he also had sciatica kind of pain, we can calculate by these formulas that now at this moment we know that there's sciatica presented. The probability is now 7 times larger, and it's about 0.14. So that's the way how it could be applied. So we can see that the patient has, the patient has to get the sciatica together with the alveolar device, so this is about 0.14. As I told you, still it's not so high number, but definitely many times higher than at the very beginning. So I would say that because what I read in one of the papers, if the probability of let's say, the possible probability of possible surgically important disc herniations more than 10%, then it's supposed to be like a relatively dangerous kind of situation, and some other kinds of examination must be done, for example, MRI or CT, definitely, just in order to rule out the diagnosis of the herniation or confirm the diagnosis, definitely, because 2% are like the prevalence, like the I would say that me or you at this moment, like for example, sometimes both me or you have you got let's say back pains, so it could be said that our prevalence is to have this generation is about 2%. It's like the general population prevalence, something like this. Yeah, we have like a, okay, maybe this is a little bit high because it's just acute kind of back pain, but sometimes I believe that sometimes you also get acute kind of back pains, but it's just going to disappear after some time. But it is together, yeah, related to sciatica. It's sometimes higher, and it could be followed by some other kinds of diagnostics processes like CT or MRI. Okay, so it was just for the example of the bias theorem. As I told you, I think that you are not going to do it on a daily basis, but for example, it will be just something like which would be very complex kind of situation. Neither you nor, for example, your colleagues would know what to do, or for example, what could be the possible, or for example, what is the risk of, for example, some severe state for the patient. This kind of calculation is relatively easily to be done. Just for example, to let's say decide if, for example, some additional kind of examination should be done or not. Yeah, well, it's like, I don't know, it's like a easy, I would say it's just a easy kind of arithmetics to be done, like to decide, for example, more confident about the situation. Okay, so the measuring the accuracy of diagnostic tests, as I told you, diagnostics are absolutely imperfect, and as I told you, there are both kinds of errors. We could have healthy patients who get positive tests, was the results of tests, so they are falsely positive. Yeah, it could happen, as well as we could have, for example, patients with disease, and they could have negative tests. In such a case, these results of this are falsely negative. So both these kinds of errors could happen, and for example, to quantify, to describe this kind of, let's say, problems which are related to, which are connected to diagnostic tests, we use two terms: sensitivity and specificity. Sensitivity is a true positive rate. It means it's just the proportion of patients with disease. So these patients have disease. So proportion of patients with disease who have a positive test results. So sensitivity is, so if we have patients with disease and these patients will have positive test results, that's okay, because it means that the test works properly, and the test is could said to us that okay, the result is positive, and very likely the patients have the disease. Similar to this, the specificity is a true negative rate. So it means that the proportion of patients, it's simply the proportion of patients without disease. So these patients have no disease, or no, at least no disease of our interest. So patients, they have no disease, but they have, and also they have negative test results. It's also okay. It's also all right. It means that it also means that the test works properly, adequately, and yeah, patients with no disease should have negative test results, of course. So if we so both the high sensitivity and high specificity is something which we would like to have within our tests, definitely. So the an ideal diagnostic test would have both the sensitivity and specificity equal to 1. Yeah, but this is only a theory. Yeah, it's only there. Unfortunately, this is not like a real situation. Okay, there are some tests which are, for example, very accurate, and their sensitivities or specificities are pretty close to 1. But still, yeah, I would say, for example, some kinds of molecular tests, some genetics tests, they are, for example, very sensitive and very specific. Yeah, for example, but honestly, for daily practice, these kind of tests, like a genetic test, they are very rare. They are not so much applied for daily practice issues. Yeah, you know. Okay, so this will be like the ideal state, but definitely in a real practice, we are not so much close to this ideal state. And you know that, for example, the real solution is somewhere, for example, about 0 at 98, or and specific could be somewhere at 0 at 99. This is like very high sensitivity and very high sensitivity. But still, there could be some possible errors, some possible reasons by which the test could fail. Yeah, could fail to show the right result, the correct result. So it could return false positive or just false positive or false negative result. So this is also some kind of example which is, for example, important to know, or it's just simply good to know about it. So supposing, well, let's suppose that you have a patient which that is suspected to have a low prevalence disease. So I would say it's a kind of a rare disease. Yeah, for example, could be a simple rare disease. Some kinds of rare diseases are very severe. For example, HIV, like a human immunodeficiency virus, and it's not like a disease. It's like a virus and just kind of infections. But it could be developed as it's like acquired immunodeficiency syndrome. So this is not rare, but absolutely severe for the patient. Okay, so supposing we have patients with to have a low prevalence disease, and the patient had it with a positive test result. So the question is, if we have a patient with a positive test result, what is the true probability that the patient, in fact, has the disease? So in other words, how likely does the patient have the disease? I think the result of this example could be really surprising for you, because the problem is, if we have a low prevalence diseases, that this like the absolutely the most the vast majority of all diagnostic tests are they could work well with if for example their sensitivity is somewhere around 0.98 or 0.99, and the prevalence of the disease is like a normal, for example 10% or 1%. These numbers are still relatively high, but considering that the prevalence is relatively rare, and maybe from the genetics that we call the disease as a rare one if the prevalence is below below this, like it's just it's just 1/10,000. Yeah, 1/10,000. Sorry, this is 1/100,000. Then it's just 10 power to minus 5. Yeah, the prevalence is equal to 10 power to minus 5. Then it's called considering the genetics definition, then it's called like a rare disease. So let's assume that we have just this kind of prevalence. P is equal to 0.00001. So it's absolutely pretty close to 0. For example, if there will be 0, there will be just 10 power to minus 4. It will be just the estimation of a prevalence of HIV. Yeah. It's just the 10 power to minus 4. If it's just 10 power to minus 5, it could be, for example, it's kind of genetic syndromes, or something like this. I would say I don't know the name in English, but if you give me 1 second, I can try to translate it. Yeah, this, but I have to translate to English because I don't know the English equivalent for this. Yeah, sickle cell disease. I mean, I think that this is somewhere around like the prevalence of the sickle cell disease is like 10 powered to minus 5. So it's relatively rare, but okay, still it's rare, but it's relatively severe. It would be rather severe for the patient. Well, so let's assume that we have this prevalence, and the test is relatively high. It's 98, and the test visit is also relatively high. It's 0.99. And now we would like to answer this question: how likely the patient got the disease once we got a positive test result, and the test and the prevalence of the disease of the suspected disease is yeah, just 1 over 100,000, and this is 0.98, and so this is 0.99. So the probability, I just call it conditional probability, but that's not necessary. So the conditional probability the patient has the disease is equal to this term. So we are just going following this formula, like the basic definition of probability. We are going to calculate this. So in the numerator, there is just a probability of a positive test while having the disease. So we have a patient who got the positive test, and also we are going to suppose that it's just like our event A, yeah, that he also got the disease of our interest. And in the denominator, these are the probabilities of positive tests. And this is what we are going to work on, probabilities of a positive test, because we can try to rewrite this formula in this manner. So probability of positive test while having disease. So if we have a patient and the patient has got the disease, then what are important, or how are the possible ways he could get the positive test? So if you have a disease, then it means that and the test is and the test works well. It means that if the he would get the positive value in case that yeah, in that the sensitive. Okay, we know that the sensitivity is simply the true positive. Yeah, so the true positive rate. So if the sensitivity is like 0.98, means that 98%, 98% of all patients with the disease will get the true positive result. So true positive rate is simply the product of the sensitivity and the probability, the prevalence. Yeah. Because the prevalence means that this is just simply the probability that the patient will got the disease, and this is the probability that if he got the disease, he will get also the positive result. So the true positive rate is simply equal to this. And what about the probability of positive test? This is just the clue. This is the tricky part, because the probability of a positive test could be done by two, let's say, independent situation. We can get positive test by two independent let's say, reason from two independent reasons. The first one is a true positive rate. This is the correct. This is the expected one. This is like the yeah. This one is okay, because the true positive rate is something which we are able to calculate. True positive rate is definitely if we have a patient with diseases and these patients are going to have positive test results. So it's just true positive. So it's simple. They got the disease, so they got the disease with the probability P, with the prevalence P, and the test is going to work with them. So the test is going to return the positive test result. So this is the first term before the plus sign stands for true positive rate. It's simply the same as in the numerator. Yeah, it's simply the same as the numerator. And the second term in the denominator after the just behind the plus sign stand for false positive rate. And what is important here? Because the false positive rate means that we have a patient with no disease, but still the test is going to return a false positive result. It means that we have a patient with no disease. So while the if the P stands for the prevalence of the disease, then 1 minus P stands for the probability of having no disease, having no disease of our interest. And if we this is like the probability of having not having the disease, but still this is like the terms which stands for the false negative rate. So sorry, for positive rate. If we know that the specificity stands for true negative rate, So there is a proportion of patients without disease who have a negative test result. So then the term minus one minus specificity stands for proportions of patients without disease who have a positive test results. It's just a kind of complement to the universe, to the universum of patients without disease. So the proportion of patients without disease who have negative test results, just specificity, sorry, and one minus specificity. Then consequently stands for the proportion of patients without disease who have a positive test results, and so they have no disease, but still they will have a positive test result. So they will have definitely a false positive test result. So I have to calculate 1 minus specificity to get the false positive rate, yeah, and I have to multiply it by the prevalence of having no the disease. So it's just a probability of having no having this disease. So if I'm going to replace these symbols by numbers, so S stands for 0.98, prevalence is 1 over 100,000, and this is in numerator, still is here, still yeah, the same is here, and 1 minus specificity is 1 minus 0.99, so it's just 0.91, 0.01, sorry, and finally the prevalence is 0.0001, and 1 minus prevalence is also equal to 0.09. Yeah, not just that there is 9 digits. Yeah, this is almost 1. If we are going to calculate this, we are going to get this probability. I would say that this is absolutely surprising, because you know, we as physicians usually believe the test, like we know that the tests are imperfect, you know, but you know, we just suppose that okay, maybe in 1%, it is going to fail in 1%, something like this, 1 or maybe 2%, something like this, or maybe 0.5%. But if we are going to ask the question in a bit different manner in this form, it means that how likely does the patient have the disease, considering that he got a positive result of the test, then this conditional probability. Yeah, so we know that he already got the positive test, but we suppose that the disease of our interest, for which we tested the patient, is a low prevalence. It's a very, very low prevalence, so it's a kind of rare disease. Supposing it's a rare disease, then supposing that he got the positive result of the test, there's some very, very low probability that, considering that regardless of the fact that he got the positive test, still the probability he got the disease, he also got the disease, is very low, and it's something like I don't know. I would say that it's just like yeah, just 1 promille, maybe one 1/10 of a percent, something like this. So it's pretty close to 0. Yeah, pretty close. So even in the case that we got a positive test result for our patient, it's absolutely unlikely that he also got the disease. And I would say this is really interesting. It's really surprising. So this is absolutely something which is good to know about. For a rare disease, usually our tests, so let's say up-to-date tests, are going to fail for the rare. Even up-to-date tests are going to fail for low prevalence diseases, and it's based on mathematics. So even in the cases that we have so good sensitivity and specificity, you can, for example, try to recalculate, for example, with an even higher specificity. For example, let's suppose that the 0.999, something like this. You can try to recalculate. Still, you'll get something like maybe 0.001 or something. Still, it will be absolutely close to 0. So the true probability that our patients got the disease at the moment that he got the positive test results, it's relatively low. Yeah, the probability is still low, very low, and it's such a case that if the disease is so much rare, it's absolutely yeah, it's very unlikely that he really got to this. And why it's very unlikely? Because of the low prevalence. Because it's if the prevalence is so low, it means that it's absolutely unlikely that whoever, regardless of the test result, regardless of whether the test result is positive or negative, it's simply so much a situation to meet a patient who could get this disease because of this is a one from a hundred or thousand of patients who get the disease. Uh, Regardless of the test results, it could be either positive or negative. Yeah, it's very unlikely that our patient can have the disease. So it's good to know about this. Yeah, it's good to know. So it's something like a cruise of low prevalence diseases and our nowadays imperfect diagnostic test. And I would say that this is something which couldn't be, for example, improved easily by some, for example, improving of sensitivities or specificities. Okay, this is the way how it could be improved, of course. But if the prevalences are so low, like this one, for example, then you can try to, if you are going to, for example, to do some, let's say, arithmetics with this formula, you can, for example, think about it, that the degree of this, simply the degree of this number is pretty similar to degree of this of the prevalence. So it's rather based on the low prevalence than, for example, the rather than the fact that how high are the both sensitivities or specificities of the test. So this is like something which will be just a problem even for the next generations diagnostic tests. Okay, so this is good to know about. Another part, and we are slowly moving towards the end of this lecture, is about just choosing of an appropriate diagnostic test. So basic principles. This is like the basic principle, which is not so much based on some statistics or probability or whatever. This is something definitely we are going to study, for example, in internal medicine or in whatever other kind of subject courses. So diagnostic test should be performed if and only if should be it. Sorry, it will likely change the patient's diagnosis or prognosis or therapy. So it means that in a situation that, for example, we would say, okay, uh, it's it's not so much important for us, for example, to get the result of, for example, the supposed diagnostic test, because regardless of the result of the diagnostic test, we are going, for example, only to apply some watch and wait strategy for our patient. In such a case, it's absolutely not necessary to do the diagnosis. You know, if regardless of the result of the test, if we still follow, for example, with the watch and wait strategy, it's absolutely yeah, it's just a waste of money and waste of time to do the diagnostic test. You know, so if we are not willing to change, for example, our current treatment or our current um, attitude to prognosis or therapy strategy, there is no reason to start or to do any diagnostic test there. It will be only kind of academic examination, something like this. Yeah. There's no pragmatic reason to do it. And how to decide? Okay, it's something which is like yeah, it sounds absolutely clear, yeah, but how to realize how to realize when it could be important, for example, because no one can know, for example, if the diagnosis will be, for example, so much yeah, for example, the result of the diagnosis will be, for example, so much surprising for us that we could, for example, change the diagnosis or change the, for example, apply therapy or apply treatment just after the moment that we got this kind of surprising result of diagnosis. So still there could be some kind of exceptions, because you know medicine is a very complex kind of science. So it means the kind of situation that we could, for example, change our mind after the after the test, after the result of the test. So yeah, but how to get how to realize what to where to indicate the diagnostic test. Okay, where to start to do, where to do the test. Okay, there's something which is called threshold model, threshold theory, and this is usually applied to this kind of problem. It could help to us to let's say decide whether to do the diagnostic test or not. So you know that the probability, yeah, like the physician is sure enough to start a diagnostic. Yeah, okay, simply. If you have a physician and supposedly the physician is sure enough to start a diagnostic or therapeutic process, then this probability, when the person is just got sure enough, is called the threshold. Okay. This is like the probability, it's called threshold. It could be it could be one of a different number since it is a probability, so it's somewhere in between 0 to 1 inclusively. Okay, so this will be very easy. So let age be all the harms or the diagnostics or the treatments of patients who do not have the disease. So this is like kind of, okay, this is a kind of, let's say, a situation we would like to, of course, like to avoid if possible, that we have patients who do not have the disease from some kind. We, for example, still don't know if they why if we don't know that they don't have the disease, but so these are just patients who don't have the disease, and it means that any diagnostics or treatments could harm them. Yeah, definitely. So age is just the units of this variable could be, for example, it could be transformed to some. It depends. It could be, for example, to transfer, for example, some time or money or some currency, or yeah, it really depends. It depends, for example, on the fact if you are more interested in, you know, yeah, just in money or time or yeah, just cost benefit analysis, you know. So it depends. It depends. But supposing that it could be yeah, it could be also both. It could be like the for example money time or something like for example dollar minute or something like this because the patients for example will be harmed by the fact that for example if we have to undergo some diagnostics or unnecessary non-necessary treatments. For example, they have to skip their jobs for some several days or something like this, and definitely they are going to get something like a surplus. Yeah, definitely. So they are going to lose some money, which could, for example, gain. Yeah, so it will simply measured in money currency. So yeah, it could be measured in this. So these are just the harms, yeah, and we can try to for example measure it in like in money, such that the patients could make this money instead of, for example, this unnecessary diagnostics or treatments. So these could be the definition of harms, but it depends. In other kinds of situations, it could be defined a bit different. And the B term is the B term is simply the benefits of the diagnostics or treatments for the patients who have the disease. It's pretty clear. If you have patients with the disease, so these patients have the disease, then B is measured in benefits of the diagnostics or treatments which could be applied to them. Definitely. Simply, it could be also measured in money, in currency unit, because we know that the, for example, patients are going to undergo, for example, some early treatment or very quickly and appropriate diagnostics and early treatment and successful treatment, then they are able, for example, to make some money. And also, this could be transferred to money, or it could be, for example, considered like if you are going to do the diagnostics as soon as possible and as well the treatment as soon as possible, we are going to, for example, to save some money, which could have to be invested into the patients. For example, once they could develop some, for example, late phases of the disease, like for example, some complications or yeah, this some kinds of this. So just in order to avoid the complications, for example, some long-term complications, which are usually very costly, they are usually very expensive to be treated. So this could be the benefits could be also calculated as money as, for example, the saved money once if we do the diagnostics and treatments quickly enough and correctly enough to, for example, save the patients and treat the patients, for example, in some early stages of the diseases, such that we can save the money, for example, in order not to apply it, in order not to, for example, pay for some late stages and some late complications and so on. So both the terms could be applied in monies and or measured in monies, and they will be also measured in time. So, for example, if the time is what the patients are interested in, if the patient time is like the most valuable variable for them, it could be also measured like a time, let's say, spent during the diagnosis or treatments, and so forth. This, for example, so it was just time spent for the patients who don't have the disease, and B could be like a time unit, for example, for the patients who have the disease, for example, which could be, for example, safe for them, such that if they're going to diagnose and treat it early and correctly, they could simply save the time. So, for example, they could, for example, leave the hospital or very soon and something like this. So both will be also measured in time. So don't worry about the units. So it could be both in currency unit or in time unit, or also in some special units. Sometimes there are some special units like quality of life units. Yeah, this is a kind of special unit. Quality of life. It's like because our lives are usually could be usually transformed or calculated as like the for example, okay, if for example my age is let's say 30 years, I can simply calculate how many days I simply live here so far. And definitely I would say that some of the days I live so far, they definitely don't have 100% like quality. For example, I would desire. It means that this is the day before the exam of internal medicine, or the day before exam of I don't know, pharmacology. Definitely these 2 days, at least these 2 days, they weren't of a good quality. I'm just kidding, okay? But some of the days, if you're sick or you have some time pressure, under some stress or whatever, some distress, these days are absolutely not of for a good quality. And our lives could be recalculated or refined following the terms of following the definition of days of a good quality. For example, if you, for example, I would say that, for example, maybe 1 or 2% of all the days we live so far, for example, for example, they weren't of a good quality, so it means that 98% of all the days we live so far, they are, for example, of good quality. So this is the number, yeah, 98% of days of, for example, let's say 100% good quality, something like this. So percentage of our life which we personally marked as a days with a good quality. Yeah. And if we considering to us, because we are young health people, considering in comparison to us, if we have, for example, patients with some severe diseases, where they are, for example, often hospitalized, for example, yeah, or for example, they have to undergo some repeated interventions, surgeries, and so on. I would say that maybe, for example, only 60, let's say 60% of their days they have been living so far are of a good quality. And so this is like the percentage of a good quality days of your life. So this is kind of special unit. So I just wanted to say to you that there are also some this kind of special variables, this kind of special units you should know maybe all about. This is not so much important, but it will be interesting. Yeah? This is because it's really hard sometimes how to describe the harms or the benefits. So it was so for example this kind of units like days of a good quality were developed in order to overcome these difficulties, how to define what are the harms, what are the benefits, how to measure it, what units we should use, and so on. The threshold is as the threshold that should be is sorry the threshold is h over h plus b. It's as easy as this. It's this simple fraction h over h plus b. So it's, in the numerator is h, in the denominator is h plus b. So what does it mean? Just a small example. I'm sorry. So let's suppose that we have a non-invasive diagnostics tools, for example, with absolutely negligible risk of damage. Let's say one such of such of tools is, for example, MRI or ultrasound or maybe Doppler, something like this. They are definitely non-invasive, and the risk of damage is also a negligible one. So it means that the harms are definitely very low. Harms are definitely very low. They are pretty close to zero. Yeah, and definitely the benefits for the patients with diseases. They are absolutely they absolutely exceed the harms of the patient with no disease. It could, for example, be, for example, by treated by mistake or diagnosed by mistake, for example. So B absolutely uh, exceeds many times the H term. It means that the H over H plus B, which is the threshold, this is definitely very low. This is pretty close to zero. Yeah, pretty close. So it's close to zero for MRI or ultrasound or whatever. And it means, besides other, there are of course some other reasons why to use MRI, but this is also one of the reasons why MRI has various and broad indications all around the medicine. Yeah? Because of this threshold is very low. So the threshold, as I told you, the threshold is the probability or estimation of probability, such that the position is sure enough from this point of probability, from this value of probability, position just became sure enough just to start a diagnostic or diagnostic process. So since the threshold is very low for MRI or ultrasound, so it's very likely that for many patients, uh, yeah, I just feel that the probability is will be larger, or probability just probability of for example a suspicion of, for example, that the patient could have a disease will be very likely higher than this threshold. So when the probability of the suspicion of such a disease for a patient is higher than the threshold, and since the threshold is very low, because the harm is almost zero here, and B is relatively high, then H and B, H over H plus B is a very low number, and that's why MRI is something which is like indicated very often. But also there are also some other kinds, some other principles. Yeah, it doesn't mean that each patient should undergo MRI. It's also no, it would be feasible, but if you have a suspicion to some disease of our interest, let's say, and the probability of such a disease, for example, based on some literature or based on experience of physician, is higher than the threshold. And in case that the threshold is generally low, which is for MRI or ultrasound is generally low, then very likely the MRI should be indicated. Okay, the big question is where to get these numbers, for example, for common diseases or common, let's say, common diagnostic tools. Some of them are, of course, they are published in some papers, and that's the this is just the most this is the most common way how to get it. Yeah, because we have to go through literature. So like up-to-date database or Cochrane library. These two are like quantitative databases. So there will be many papers published on these topics. Yeah, so this is the way how to get these numbers. And also, I would say, like in a normal routine daily practice, you are not supposed to calculate this. This is, let's say, in such in kind of special situation that we are absolutely not sure whether to start whether to do the diagnostic, whether to indicate the diagnostic test or not. If you are absolutely not sure, and for example, your colleagues are also not sure, then in such a case, it's maybe a good time to think about this approach, to think about the threshold model approach. In such a case, it's a good example where to start to think about this, but not earlier. If this is a routine situation, forget on this. Absolutely, it will be just a waste of your time to calculate something like, because definitely are going to realize that the probability or for example the confidence you should do the diagnostics or therapeutic process will be far more higher than the threshold, because if it's just a routine, it will be just a routine situation, the threshold will be very low, because you know that the harms are, for example, acceptable or very low, and benefits are very high. If it is a common or routine situation, then it's routine because of the fact that the benefits are high and harms are low or negligible. That's it. Sutton's law, or one of the last, yeah, this is just simply the last situational, last principle you should know about. And definitely, I would like to repeat one more time that this topic is so much complex that definitely I might forgot to mention some other kind of principles or laws or whatever. But Sutton's law is very intuitive one, and it's also interesting from the point of view of mathematics. I like it, but I'm not going to bother with mathematics. Okay, I just made a mention mark about the mathematics, but forget on this. Maybe if you are will be just interested in this, so yeah. So there's a method behind this. But what is the Sutton's law about? So the Sutton's law suggests that one should first conduct those tests, those diagnosis tests, or some those treatments, which okay, this is rather about the diagnosis, or those tests which could confirm or rule out the most likely diagnosis. So it means that we have a situation that okay, we have a patient with some bunch of symptoms, and based on your experience or based on, for example, results of all the tests you got so far, for example, you are able to think about, for example, 4 possible diagnoses. Uh, and for example, you are not sure which one is the diagnosis of your patient. And based on your experience and based, for example, on your experience, intuition, and on the results of, for example, biochemistry or just a blood test and so on. You can, for example, I believe that we'll be able to, let's say, order these 4 diagnoses, for example, in decreasing order. For example, based on a probability of such that the patient could have the diagnosis. It means that, for example, the first one would be just the most likely one, the last one would be just the most unlikely one. Yeah. So I pretty believe that after some practice, after some experience or real practice, we'll be able to, let's say, think about it this way that because I'll think about 3 or 4 diagnoses, and one of them is very likely, and the rest of them are not so much likely, and the last one is absolutely unlikely, but still it could be, but it's very unlikely, something like this. So if you are able to, let's say, sort your diagnosis, your possible things about diagnosis in a decreasing order, then start to confirm or rule out the first one, the most likely one. This is absolutely what the Sutton's law is about. It's as easy as this. What is the rationale behind this? The rationale behind this is just simply, it's very simple. It's simply to minimize the length, the time length of the diagnostic process as much as possible. It's simple as this, because if you simply start with the most, for example, with the least likely, the most unlikely, it's very likely it will likely happen that the tests you are going to apply on the patient are going to rule out this unlikely diagnosis because of the fact that the diagnosis was absolutely unlikely, and you knew it before it. But okay, it's going to rule out. So you just you just lose some time. The patient could get it's a bit upset, for example, and you have to continue from the beginning. Yeah, because you have to, for example, send the patient to some other test and so on. So it's absolutely logical to start with the most likely diagnosis and to confirm it or eventually rule it out. But yeah, it depends. It depends on the results of the test. But this is absolutely. So I would say that it's absolutely intuitively. But as you know, it usually goes this way in medicine. That it also got its own name. It's named after Saturn, and I forgot his first name, but Saturn was just it wasn't. Don't be mistaken. It wasn't just a professor of medicine. Absolutely not.